Welcome to The Explainer, where we break down big ideas. Today, we're going to tackle a really clever math concept called partial fractions. Think of it like this. It's about looking at a fully baked, complicated cake and figuring out the exact simple ingredients that went into it.
Okay, so to get our heads around this, let's start with something we all know how to do, adding fractions. We're just going to look at it in a slightly new way. So imagine you've got these two simple ingredients, these two fractions right here. To combine them, you know the drill, right? You find a common denominator, in this case it's just x minus 3 times x plus 2, and then you add the tops together. And after a little bit of algebra, you end up with this single, much more complicated looking fraction. So we went from simple building blocks to a complex result, from flour and eggs to a cake. But what if we only have the finished cake? I mean, this is the real challenge, and it's where all the magic really happens, figuring out how to work backward from that complex result. This right here is the core question. If I just gave you that cake, could you tell me exactly how much flour and how many eggs went into it? That is the puzzle we are trying to solve. This whole reverse process actually has a name, partial fraction decomposition, and it's pretty much what it sounds like. Our goal is to deconstruct, to, unbake the cake and find those original, simple ingredients. So how do we actually do it? I know it might seem like a total guessing game, but thankfully, there is a clear, logical blueprint we can follow every single time. And here it is. This 4-step blueprint is our guide. It gives us a totally reliable way to solve the puzzle for any fraction, turning what looks like a mystery into a really straightforward process. All right, let's put that blueprint to the test and do a little detective work with an actual example. Honestly, seeing the steps in action makes all the difference. Okay, here is our mission. We need to break this fraction down. So following step 1 of our blueprint, the very first thing we do is set up what we think the answer is going to look like. We just assumed that it came from two simpler fractions, one with a denominator of x plus 2 and the other with x minus 1. Now, a and b, those are our missing numbers, the mystery ingredients we need to find. Now for steps 2 and 3. We multiply everything by that original denominator just to get rid of the fractions. Then we expand everything and group all the x terms together and all the constant numbers together. What we get is this really critical equation. The key insight here is that the left side and the right side must be perfectly balanced no matter what x is. And now for the really crucial part, we match the coefficients. The number in front of x on the left side is 3. That has to equal the stuff in front of x on the right side, which is a plus b. And hey, the constant number on the left is, 0, and that has to equal the constant on the right. This gives us a system of two equations that we can totally solve. By solving this pretty simple system, boom, we found our missing pieces. A is 2 and B is 1. The secret recipe has been revealed. But what if I told you there's an even faster method? At least for cases like this one. It's a fantastic little shortcut. Sometimes it's called the Heaviside method. We can actually pick strategic values for x that make parts of this equation just vanish. It's a really elegant way to isolate our unknowns. Just watch this. If we choose x equals 1, the entire a term becomes 0, right? Because 1 minus 1 is 0. This instantly leaves b all by itself, and we find that b equals 1. No system of equations needed for that part. And we can do the exact same thing for a. If we choose x equals negative 2, the b term just disappears. And that lets us solve for a just as quickly. So the point is, we get the exact same answer, a equals 2 and b equals 1, but we got there way, way faster. And there it is. We have successfully deconstructed our complex fraction back into its original, simple parts. We have officially unbaked the cake. Okay, so that's a neat math trick, but you might be wondering, why does this even matter? What's the big picture here? Why would we ever need to do this? Well, in something like calculus, trying to work with that complex fraction on the left is a nightmare. But working with the simple pieces on the right is incredibly easy. But it's bigger than that. Breaking things down isn't just a math trick. It's a fundamental way to approach tough problems in any field, from computer programming to managing a big project. And that's our explainer on partial fractions. It's a powerful reminder that even the most intimidating problems are often just a collection of simpler parts, waiting for us to find them. So the next time you see a complex problem, mathematical or otherwise, think about how you might be able to break it down.